So we're looking in section 7.2, which is about the basic properties of rings. So we begin with theorem 7.5, which gives you some basic properties, some very basic algebraic properties for elements within rings. So if you have a group, then number one, the group has a unique identity. There's only one identity element. Number two, for equations within G, there's a cancellation property. It works on the left side and on the right side of equations, cancellation. And number three, every element of G has a unique inverse. So we knew already we knew every element had an inverse, but those inverses are always unique. There's only one inverse for every element. For every element, there's only one inverse. That's what that's saying. I guess we should probably prove this, just so we have see how it's done. It's good to see how things are done. Okay, so let's say we have a group G. Let G be a group. So number one, we want to show there's only one identity. So we always know there's an identity, right? So let E, and also let's pretend there's another identity, E prime. Be identities in G. We know every group has an identity, right? That's one of the axioms. There's an existence of an identity, but we don't know there's one yet, just one yet. So let's pretend there are maybe two, E and E prime. Now what if I take E and I start together with E prime? Let's pretend that E prime right now is the identity. E is an arbitrary element. Let's just treat E like an arbitrary element, any element from the group. And E prime, we'll focus on E prime as the identity. What happens when you take E prime times E, or E times E prime? Well, you get E, right? You get E. If E is an arbitrary element, you take an arbitrary element times the identity, you get back the arbitrary element. Okay. Now let's think of E as the identity and E prime as the arbitrary element. So if you take the identity times an arbitrary element, you get the arbitrary element, so you get E prime. So if you follow this equation from left to right, you get E equals E prime, so that means there's only one identity. Thus, G has only one identity. Okay, let's do a number two. We want to show cancellation holds. Actually, we've already proven that. We proved that, I think, in 7.1. Let's prove it again. So suppose A star B equals, it's a little red right there, A star C in G. So these elements are in G and the equation is in G. So what we'll do, we know every element has an inverse in a group, so we're going to multiply, or not multiply, we're going to star on the left sides of the equation by A inverse. So I'm going to A inverse star on each side, left side. So what I do the left side here, I have to do on the left here, coming from the left, A star, or A inverse star. Now what we can do, we can reposition. We have the associative property, reposition our parentheses, so we have A inverse. Start with A, and then start with B. And do the same thing here. Reposition the parentheses through the associative property. Okay, now I'm going to do A inverse star with A. That's going to give me the identity. So I get the identity. Star with B. Why is that? Okay, there it goes. And we're going to do A inverse star A is going to be the identity. Start with C. So that's going to be equivalent to, okay, the identity times B is B. Identity times C is C. So we get B equals C. So AB equals AC implies B equals C. So that's called left cancellation. So similarly, right cancellation holds in G. You can do the same thing. I'm not going to go through it. I'm just going to say similarly. So I think we've already done that. All right, let's do a number 3. What do we want to do with number 3? Oh, let me make some more space. What was number 3 about? We want to show every element has a unique inverse. Okay, so let A be an element in G. So we know there's an inverse, A to superscript -1 for A within G. Let's pretend there's another one. A, let's call it prime. I don't have a better symbol, so I'm going to call it A prime. That'll be the other inverse. So suppose A superscript -1 and A are inverses of A within G. Well, according to the definition of the inverse, at least part of the definition, A starred with A inverse equals the identity, and A starred with A prime. Oh, I forgot to write a prime. That should be a prime right there. A prime equals identity. So what we can do, we can set these two things equal because they're both equal to E, right? So we have that A starred A inverse equals A starred A prime. And by left cancellation, right, we have left cancellation from the part 2 of this theorem. By left cancellation, that means A superscript -1 equals A prime. So in reality, these two seemingly separate inverses are really the same. So thus there is only one inverse of A. And that's the proof. That covers parts 1, 2, and 3. Okay, so we want to follow this up with a corollary. I don't really know why this one's called a corollary. I think it should just be a theorem because it doesn't seem to follow immediately from the 7.5. So this is corollary 7.6. And it says, so more properties. These are kind of equational properties having to do with the inverse. So there are equational properties having to do with the inverse. If G is a group, with A and B elements of G, then two facts. Number 1, AB's inverse okay. Let me use the star notation. So the book doesn't use the star notation. I'm going to use the star notation. They just kind of drop their stars. They get lazy. I'm going to put A star B. Inverse is equal to B inverse star A inverse. It's convenient not to have to write that star every time, but I'm going to write it. And number 2, I don't want to be super lazy. A inverse's inverse is simply A. So we've seen stuff similar to this proven with rings when we had a field. So let's say G is a group. Let G be a group with elements A and B and G. I'm going to start with 1. Why is that not blue? It should have been blue. If I take AB, now let's take, come on, it's not working. There it goes. Let's take A star B. So we're going to find a counterpart to it, something we can multiply it by to get the identity. I'm going to take AB and I'm going to star it by B inverse star A inverse. B inverse star A inverse. So what I'm going to do, I'm going to reassociate things. So I have A star, B star, B inverse, close parentheses, star A inverse. So we got A star. Well, what's B inverse? B inverse is the identity element. And we have what? Star A inverse. So now I'm going to do A times E, or A starred with E, that's A. So we have A star with A inverse. Come on, that should be a red A inverse. Come on, turn red. There we go. A star A inverse is going to be the identity. So on one hand, when you take AB and you start on the right by B inverse A inverse, you get the identity. Let's see if we can star AB on the left by B inverse A inverse. Let's see. So I'm going to take B inverse, start with A inverse. I'm going to star on the left of AB. So I'm going to rearrange things. I'm going to leave B inverse alone. I'm going to move the parentheses really around A inverse star A in the middle. We're going to have a star B on the end. So we call that B inverse starred with, well, in the middle you got A inverse A. That's going to be the identity. And we're going to do B inverse E. B inverse E. What's B inverse E? It's going to be B inverse. And then we're going to start that with B, and B inverse B is going to be the identity. So on one hand, you take AB and you start by B inverse A inverse, you get the identity. On the other hand, you take B inverse A inverse and you start it by AB and you get the identity. So in any case, you're going to get the identity. So that means thus, A star B's counterpart, its red dude, its inverse is equal to B inverse star A inverse. Oh, and I don't need that parenthesis there, not necessary. Okay, so pretty much same thing with when we did matrices, exact same proof with matrices. So if you had like capital A's and B's. Number 2. Number 2 is to show that, what? A inverse is N versus A. So if I take A inverse, I want to find something I can star it by to get the identity. It turns out if I star A inverse by A, I get the identity. And also, if I take A inverse and I want to get the identity, what can I star it on the left by? Well, I can star A inverse on the left by A. So however you want to do it. You can star on the right by A, you can star on the left by A. That means, thus, A inverse's red counterpart is A, right? A inverse's do that you multiply by to get the identity is A. And a proof. Yeah, so that's just the same, exactly the same as when you were dealing with matrices. Okay. I think I might quit there.